Okay, here's the abbreviated recording now. We just missed an example on partial fraction decomposition, so that was totally my fault. If you want to see it and you're watching this later, let me know and I'll show it to you. All right, so still solving recurrences by generating functions. So we have, hang on, let me make sure I didn't just flip back a page. No, we haven't done that one yet. AK plus 2 equals 2AK plus 1 minus AK. A0 equals 0, A1 equals 1. Oh. Come on. Of course, I started recording and then lost focus. There we go. All right. So this is a perfect example of one that I would not normally use generating functions on. Real quick in the chat, how would you solve this if you were given the option? Here's a hint, besides generating functions, we only have one other method. Yeah, there you go, Jose. Yeah, this would be a perfect, it's a constant coefficient guy. The characteristic equation works great. And so that would be the way to actually do this. But to torture ourselves, let's let A of x be equal to the sum of AK x to the k. And of course, that's k greater than or equal to 0. So then we will multiply everything by x to the k and sum. So we get the sum of AK plus 2 x to the k equals 2 times the sum of AK plus 1 x to the k minus, that's just going to be A of x. Let me go ahead and write it out nicely. K equals 0 to infinity, k equals 0 to infinity. So now this one is actually missing 2 terms. If we think of this as, let's see, we can say this is 1 over x squared times the sum of AK plus 2 x to the k plus 2 as k goes from 0 to infinity. And sorry, let me do my little left-hand side trick so I don't have to keep track of all of it. So this is equal to 1 over x squared. And then this is A of x, except we're missing A0, x to the 0, and we're missing A1, x. We've done this piece a bunch, so when we get there, we'll just kind of know what that is. But in this particular case, A0 is 0, A1 is 1, so this is 1 over x squared times A of x minus x. So then our right-hand side, this is going to be 2 over x times the sum as k goes from, I'm sorry, somebody's decided to make crushed ice in the background. I'm just going to pause. A lot of crushed ice. Oh, okay, that's good. All right, so we're converting this piece. So that's 2 over x times the sum of AK plus 1, x to the k plus 1, minus A of x, parentheses around that just to be clean. And then that's 2 over x times A of x minus A0 minus A of x. A0 is 0 in this case. So then, if we put that together, we have 1 over x squared times a of x minus x equals 2 over x times a of x minus a of x. So multiply through by x squared, we get a of x minus x equals 2x a of x minus x squared a of x. So now we put all of that to one side, except for the x. We'll put the x over here. So we get a of x times, that's going to be x squared minus 2x plus 1. So a of x equals x over x minus 1 squared. So about that partial fractions example that I forgot to record, it's almost exactly identical to what we're going to now do. So we have a of x equals x over x minus 1 quantity squared. That's also equal, remember, to the sum of ak x to the k as k goes from 0 to infinity. And we're trying to figure out what ak was. So we'll use partial fractions on this piece and write x over x minus 1 squared as a over x minus 1 plus b over x minus 1 squared. From that, we get a times x minus 1 plus b equals x. So x equals ax plus b minus a. As a system, that is a equals 1 and b equals a equals 1. So we can rewrite it as a of x equals the sum as k goes from 0 to infinity, ak x to the k will be equal to 1 over x minus 1 plus 1 over x minus 1 squared. And then we can put that into our happy little geometric series format. This one doesn't require any negation because it's inside the square, so 1 minus x squared is the same as x minus 1 squared. The other one, we get a little negative 1 up top. Let's see. So this is equal to negative the sum of x to the k, as k goes from 0 to infinity, plus that's going to be k, oops, forgot my sum. Sum as k goes from 0 to infinity, k plus 1, x to the k. So we can combine those and get the sum of k, x to the k, as k goes from 0 to infinity. Which means that the sequence that we were solving, ak equals k. And where was that original sequence? K plus 2 equals 2 times k plus 1 minus k. That absolutely checks, right? And we have k is 0 when, or sorry, A0 is 0 and A1 is 1. So we were matching the k with the a there. Sometimes it's just nice to check in your original equation so you can make sure you didn't make a mistake. I think there was one more thing I wanted to show you guys today. Yeah, I've got time. Won't pull the page away this time. So sometimes when you are solving one of these, a little something weird happens. Let's start with this. Cn plus 1 equals 2ncn plus 2cn plus 2. C0 equals 1. That is a really weird way to write that. Well, when we let c of x be equal to the sum of c n x to the n, as n goes from 0 to infinity, then over here, we've got c0 equals 1. So this is 1 over x times c of x minus 1, right? We've done that a bunch of times, so we can just kind of skip that step. And over here, we have the sum as n goes from 0 to infinity of 2n cn plus 2cn plus 2 x to the n. The left-hand side is pretty well in good shape, so we'll just work on the right-hand side for a second. The right-hand side here, not going to do the whole thing. Let's just do the part as n goes from 0 to infinity of 2n cn x to the n. So that's equal to the sum as n goes from 1 to infinity, because when n is 0, that's 0, 2n cn x to the n. That is, well, then we can take an x out. So we get x times the sum as n goes from 1 to infinity of 2n cn x to the n minus 1. This is equal to 2x times the derivative with respect to x of the sum as n goes from 1 to infinity of cn x to the n. Remember, the c0 x to the 0 is a constant term, so I could also write that as the sum as n goes from 0 to infinity. And so this is just c of x, so this is 2x times c prime of x. Then continuing, so that's the first piece. Now for that part, we just are going to get the sum as n goes from 0 to infinity of 2cn x to the n is 2c of x. And then, of course, the sum as n goes from 0 to infinity of 2x to the n is just 2 over 1 minus x. So to put this back in our equation, we get 1 over x c of x minus 1 equals 2x c prime of x plus 2c of x plus 2 over 1 minus x. And so that's a little bit of a problem, because that's a differential equation, and as I'm sure some of you would like to point out to me, differential equations is not a prerequisite for this course. So, and in fact, this is not the prettiest differential equation it could be. It is linear and first order, but it is non-homogeneous. It could be done using methods from our differential equations class, but it's not what we want to do today. So if when you do this with ordinary generating functions and you get a differential equation, you can try it again. So just, I'm gonna rewrite everything up here so we don't lose it. C0 equals 1. But instead of letting our C be an ordinary generating function, let's let h of x be the exponential generating function for our sequence. Now, there are some downsides to this. We are going to have to be really careful when we reindex because we need that x to the n over n factorial in order for it to be in a exponential generating function, and we've got to deal entirely with exponential generating functions. So now let me rewrite this as 2 times n plus 1 Cn plus 2. It'll just make our lives a little bit simpler. So then the left-hand side, or sorry, we'll do the whole thing here. The sum as n goes from 0 to infinity, Cn plus 1, x to the n over n factorial equals the sum as n goes from 0 to infinity of 2n plus 1 Cn x to the n over n factorial plus the sum as n goes from 0 to infinity of 2 x to the n over n factorial. So the left-hand side, is still h of x minus C0. Let's see. Nope, no 1 over x. Hang on. Let me see. Let me actually do the calculation out. So if I want to write this as oh, that's the trick I pulled here. Sorry. So this already had an n plus 1 in it, and that had an n plus 1 in it. So I actually, this step was supposed to say the sum as n goes from 0 to infinity is Cn. Instead of multiplying by x to the n over n factorial, we want to use x to the n plus 1 over n factorial. It will make our lives much simpler. I think we could have gotten there from here, but it would have been a lot of multiplying and dividing by n plus 1 and things like that. So this just kind of gets us there a little quicker. 2 to the n plus 1 Cn x to the n plus 1 over n plus 1 factorial plus the sum as n goes from 0 to infinity of 2 x to the n over, or sorry, x to the n plus 1 over n plus 1 factorial. This is still n plus 1 factorial. There we go. So now, and this was already a plus 1, that's from the left-hand side. So this guy right here is just h of x, except it doesn't have the C0 term. So that's h of x minus C0. That's the left-hand side. The right-hand side, we have, let's see. So if I take and cancel, let's pull out an x. This is the sum as n goes from 0 to infinity of 2 Cn. So I've pulled an x out, and I'm going to cancel the n plus 1 with the denominator there, and then I get x to the n over n factorial. Plus, this is just going to be 2e to the x minus 1 in parentheses. So the right-hand side is x. this is times 2 times h of x plus 2 e to the x minus 1. Putting that all together, we get h of x minus c0 is 1 equals 2x h of x plus 2 e to the x minus 1. H of x then is equal to, h of x times 1 minus 2x is equal to 2 e to the x minus 1. Dropped the parentheses, distributed the 2, but then added the 1. So let's see if I can transfer this. So h of x equals 2 e to the x minus 1 over 1 minus 2x let's see. 2 e to the x would be, or let me use this here. So e to the x is 1 plus x squared over 2 plus x cubed over 3 factorial, and so on. So 2 e to the x is just double that, right? And so 2 e to the x minus 1 is 1 plus 2x squared over 2 plus 2x cubed over 3 factorial, and so on. And 1 over 1 minus 2x is 1 plus 2x plus 2 squared x squared plus 2 cubed x cubed, and so on. So the coefficient, so for n greater than or equal to 1, the coefficient of x to the n over n factorial is, these were ordinary generating functions, right? The way I wrote them this way. So this is n factorial times 2 to the n plus 2 times 2 to the n minus 1 plus 2 times 2 to the n minus 2 over 2 factorial plus 2 times, dots here, and then 2 times 2 to the 1 over n minus 1 factorial. This is just the convolution, but we tacked the n factorial on the front, plus 2 over n factorial. So that's equal to n factorial times 2 to the n plus 2 times the sum as I goes from 1 to n of 2 to the n minus I over I factorial. So we have to be careful because we get, this is a 1 instead of a 2. That's why this guy is a little bit different from everybody else, and that's why we have to peel, oh, shoot. Where was it? It was there. Okay, so n factorial equals 2 to the n plus 2 times the sum as I goes from 1 to n of 2n minus I over I factorial. This part represents all of these, and we just have to have a separate piece for the front because since that was 2 e to the x minus 1, we don't have a 2 here, even though we have it everywhere else. And we can check a couple of terms here. For C1, let's see, what was our C1 equals, according to this, 1 factorial times 2 plus 2 times 1 over 1, which is 4. And if I use the original equation, then C1 equals 2 times 0 times C0, which was 1, plus 2 times C0, which was 1, plus 2, and that checks. And we can check it for C2 while we're at it. So C2, we get 2 factorial from this formula, 2 factorial times 4 plus 2 times 2 plus 1/2, which is equal to 18. And if we do it this way, C2 is equal to 2 times 1 times C1, which was 4, plus 2 times C1, which was 4, plus 2, and we get 8 plus 8 plus 2 is 18. That last step is really just a check step. That's it for generating functions, for recurrences, all of that. I'm gonna start going through some special topics on Wednesday. I have some graph theory things I haven't shown you, and they're adjacent to current research topics. I think that's kind of an interesting thing about graph theory. It's been a while since I've mentioned this, so I get to say it again. One of the coolest things about graph theory is that the distance between a student and a research problem is so much less than in other fields. Like a student of graph theory, it's just such a new field that, I mean, there's a lot out there, but it doesn't take long to bump into a problem that people don't know the answer to yet, which is pretty cool. So I'm going to show you some things that we do know and some things that we don't know. Anybody have any questions before we run out for today?